Good afternoon, everyone. I hope everybody had a very good lunch break. We are going to resume our final session of today's set of presentations. My name is Lisa Forbes, and I will be chairing this afternoon's session. And our first speaker is Mansour Edraki from the Sustainable Minerals Institute. Go ahead, Mansour.
Thanks very much, Lisa, and thank you, Rick, and all the organizers for a really interesting day of talks. I would like to thank all the people involved in this project. So Artem, Anita, and Gordon, and Mehdi, and two really good, talented PhD students, Zhengdan and Amelia. So this project is focused at Mount Carbine, which is located in North Queensland. So this is one of the abandoned mines that we have been working on. I've worked on a number of these abandoned mines in Queensland over the last few years. And the focus is really on environmental geochemistry, understanding the environmental issues, but at the same time look for opportunities for potential recovery of elements of value. And of course, you know that the project that Anita is running, focusing on critical elements, which is important and for the industry and very topical at the moment. At the same time, we don't really know much about the environmental side of critical elements and the toxicity and the mobility and the environmental geochemistry of things like tungsten, for example. There is not much published. Recently, there was this paper in Chemosphere that was focused on understanding the mobility of tungsten. And the motivation for that was, there was some correlation between tungsten concentrations in some natural sediments in a few locations in Western United States, in 3 states, and with a child leukemia. So that was the motivation of that study. And in fact, it was really interesting to see, I just saw this paper recently that some of our findings is actually consistent with what they have found. For example, that, with increasing pH, we have more monomeric tungsten ions, tungstates in an oxyanion form that they adsorb to iron oxyhydroxide. This is the situation that happens at Wolfram camp as well, which I will show you in a minute. So as I said, there are a number of these tungsten mines in Queensland, the important ones such as Mount Carbine here and Wolfram camp, which is the focus of this study. Wolfram camp is about 120 kilometers from Cairns, and it is located in a semi-arid subtropical climate, very typical of that part of Queensland, with open woodland vegetation and native grass cover with negative water balance, obviously. And you can see that some of the pioneering plants start to come and populate some of the waste storage facilities on site. So there is a long history of mining on that site. And the most recent one was done by Almonte, that company which closed operation. And in 2018, the NRME declared that site as abandoned. The geology of the site is dominated by wolframite, molybdenite, and bismuthnite in granite granite near the contact with sedimentary and volcanic rocks. So you can see that in that cross section, the location of the ore bodies. And the type of processing included X-ray sorting, so there were X-ray sorting machines on site. And through gravity separation, they separated wolframite concentrate, and then flotation, they used flotation to take out molybdenite. This is a photo of the site in 2013. You can see here the tailings storage facility, and then the second tailings storage facility. This is the tailings down wall. Here at the background, you can see the pit, and you can see a view of the kind of vegetational landscape in that environment. Then later on, they covered the tailings with rejects from the ore sorting. So this material is well sorted, and that's a problem because that has high hydraulic conductivity. and infiltrates, the water infiltrates into that. And then they took some of the material excavated from the tailings to create more space and also to stop overflowing and contaminating downstream from the tailings. And they put them here and started to dry them. So this is an aerial photo of the site at the current time. You can see the pit, the rejects, some of the waste rock dumps, the PAF material, the tailings storage facility, and the water dam down there, the downstream. And there is a diversion channel here which separates good quality water from contaminated water. Nevertheless, there is seepage and runoff from tailings, so this dam is very contaminated. And this is another view of the site. And the pit water, as you can imagine, is acidic with a lot of sulfate and high EC and other kind of metals in it, and including fluoride. And the water dam, again, because it receives water from the waste materials, leaching of the waste materials, so very low pH and high conductivity and sulfate. This just shows the very deep profiles within the tailings storage facility and the dumping of the rejects on top of the tailings that has created acid mine drainage situation. And this is some of the tailings that are drying on top of the rejects. So we did a number of profile sampling in that site. And the interesting thing is that the profile of the tailings here are slightly different from what you normally see in a sulfidic mine. So you'd expect an oxidized zone, and you go deeper, you get to the more grayish unoxidized material. Whereas here, because sulfide is not the dominant mineral, we have wolframite. And then because the mineralogy, which is granite mineralogy, so you get adamelite, you get more plagioclase, the kind of, those kind of color minerals. So it's a mix of oxidation products and also and the true color of gangue minerals. Nevertheless, in some horizons, you see when you have high sulfide concentrations, you get accumulation of secondary minerals and iron oxide, jarosite, and that kind of material in the profile. Also, because of the accumulation of wolframite and also deep weathering and oxidation, you also get some of these hard pan layers form in some of the profiles. So the tailings generally are sandy, low, sand and fine sand and some silts. And quantitative XRD doesn't pick up wolframite, but you can see, the typical granite mineralogy with some secondary minerals and also some sulfides. The hard pan layers obviously have more pyrite, more jarosite, goethite kind of secondary mineral forming there, and more clays in some instances. But this is a shot of so this is concentrate. This is not tailings. Nevertheless, it's the same. The concentrate that they produce. So you got wolframite there and pyrite. But MLA clearly shows the mineralogy and texture. So this hard pan layer is better because it's more concentrated. So you get more concentrations of molybdenite is very common on that site. But we also have wolframite and very, very small amount of scheelite. So this site is not a scheelite site, it's a wolframite site. But there are sites in other parts of the world that, the tungsten tailings and they have a lot of scheelite in them, for example, in Sweden. Now, the chemistry of tailings show that they are very high concentration. They contain high concentrations of arsenic, molybdenum, nickel, lead, tungsten, uranium, cadmium. More than higher values, the median values are higher than the rejects and waste rock dumps and low grade ore. The geo-environmental indexes that we calculated again are high in arsenic, things like arsenic, bismuth, molybdenum, tungsten. The enrichment factors that we calculated based on normalizing the values with the crust and using aluminum as to normalize the values. And in fact, here in these graphs, you can see the abundance in granite and the abundance in crust for those elements. So you can see the these elements, they're toxic, they're elevated, but some of them may have economic value as well. But we talk about tungsten in a minute, but you can see that very high elevated concentrations of all these elements. Nevertheless, when you compare them with NEPM guidelines, it was arsenic that was be above the threshold for healthy investigation. But I have to say that there is really no guideline for tungsten, and a number of these critical elements we don't really have a good understanding of their mobility and toxicity, and also there is no guideline for some of these critical elements. In terms of economic concentrations, when you compare the Wolfram camp tailings concentrations, grade and tonnages with a few around the world, a few tailings storage facilities around the world, you can see it's relatively low. And then compared to Mount Carbon is slightly higher. So this on the right-hand side, you can see compared to the low-grade ore and rejects on site, the values of tailings are relatively lower. So the rejects and low-grade ore are obviously a better prospect for processing. So we need to understand the mobility of tungsten. The first thing is to look at the profile samples and see the co-placement and co-location of tungsten with a number of other elements. And so in this case, for example, on the profile, this profile, when you look at zinc, because zinc is very mobile, so you can see it doesn't really follow a predictive pattern. Whereas when you look at iron and tungsten, there is some correlation, but whether this correlation relates to just being placed at the same time and having high concentration, or there is a chemical process, this is where we need to do sequential extraction and try to understand the mode of occurrence of that element of interest. So whether we want to understand whether it's water soluble, is it exchangeable, is it weakly acid soluble, weakly reducible, whether it is associated with iron oxide or sulfides or residual silicates. So that's why Zheng Dong, the PhD student, has done a fantastic job, gone through this process of sequential extraction. And what we found that tungsten is similar to that study in US. So tungsten is associated with the iron oxide fraction, and even more the more stable fraction of iron oxide hydroxide. So things like goethite, for example, as opposed to ferrihydrite. So arsenic, tungsten, and bismuth are mainly associated with iron oxide hydroxide fraction. Whereas manganese, for example, is associated with the water soluble fraction. So you can see in that blue color. And rare earth elements were associated with the residual fraction in a silicate form. So this is important both from the perspective of toxicity and potential mobility, and also the perspective of potential extraction. As I said, it's really interesting to see that tungsten at that kind of pH formed this monomeric tungstate form, and it is absorbed to this tungstate ion is absorbed to ferrihydride. It starts absorbed to ferrihydride, which is less stable, and gradually to more stable phases. And then you can see that it forms an oxyanion, just like arsenic, and absorbed there. And then as the ferrihydride starts to lose its water, it becomes more stable and associated with that fraction of iron oxide or manganese. So that's the stability around here for tungstate ion. Now the issue of acid mine drainage at that site, on the left-hand side, you can see that all the data for net acid generation potential and net acid production potential, these two different tests that shows that tailings, most of them are non-acid forming, or NAF, you can see here. Most tailings are non-acid forming. Some of them are uncertain, and we probably need to do some column leaching. But we know from the mineralogy and the geochemistry that there is very little sulfide pyrite in there. But because the gangue minerals are granite, there is not a lot neutralizing capacity. but we don't think that this acidity relates to tailing. It's really more related to this well-sorted material here that is dumped here, and water is sprayed on top of it. They're trying to get rid of the water coming from the water dam, just trying to reduce the level of water there. So they're spraying and evaporating water there. So it's important to understand. But the other interesting aspect of it that Zhengdang is working on under supervision by Gordon Southam is looking at the bacteria. So as I said, sorry, here this shows that the sums inside the tailings, the storage facility have low pH, but that low pH is because the water is going through the rejects and is not being neutralized by any, there's not neutralizing capacity in the system, in the tailings. So the pH remains at low pH, acidic pH. Anyway, so Zhengdang has been looking into potential bioleaching. Firstly, understand the bacteria there, indigenous bacteria, the ion oxidizing and sulfur oxidizing bacteria in that system, and to see if there is an opportunity to do some bioleaching. And so he has been working with Gordon and looking into samples of sludge, biofilm, sediment, and rock, and try to identify the bacteria. And which in that SEM image you can see some of these ion oxidizing bacteria on the surface of these AMD materials. And he has been also running a few samples, looking at both the rocks and tailings, and doing these column bleaching experiments in syringes to look into whether if he adds nutrients and adds the bacteria, the material that he's got from the site, into inoculate them into these tubes to see if he can leach some of the metals from the tailings and also from the rocks. And he has got some interesting results. So this slide is a bit old, so he has more data now. But generally speaking, you can see that he's been able to leach arsenic and some uranium and copper, not much of tungsten. The focus of Zhengdang's work is really more understanding these opportunities rather than trying to solve the problem of that particular site. But nevertheless, these are interesting things. One could potentially decontaminate some of these tailings and then use the material for rehabilitation. So that's one opportunity. And we also did some
Mansour, sorry, 2 minutes, please. 2 minutes, please, Mansour.
2 minutes? Mm-hmm. Okay. So we also did some physical separation tests. Most of the tungsten was, this is a tungsten assay by size, and most of tungsten is accumulated in the fine fraction. And so we ran some what they call super panning, which is gravity separation method to separate. So we created the concentrate from the finer fraction of the tail, and we produced concentrate, which has about 22% tungsten oxide. So these images at the bottom show we have coarse material, sandy material with a lot of quartz in it, which can be used for capping material for cover. We have fine, benign clay material that can be used as a sealing layer, and then we have a concentrate which has tungsten in it. And so that's a very simple flow sheet that we can use gravity separation and followed by flotation. This is a system. This is a process that is happening at Mount Carbine, and they're getting some good results. What we are interested in is that where in the system, where in the process, we can separate materials that can be used for establishment of vegetation and also for capping material for rehabilitation. Artem did some high-level costing, and he found that based on the prices of tungsten, we can probably make $6 million from the tailings and $18 million, the total amount of waste, processing the total amount of waste on that site. So in conclusion, tailings will continue to leach contaminated seepage if left uncapped, and particularly if covered by rejects. Some contaminants have been attenuated by secondary iron minerals and amorphous phases. Some contaminants are readily available and can be easily mobilized. The environmental consequence of the dispersion of some of these critical elements, such as tungsten, is not well understood globally. The overall grade of elements of economic interest is relatively low compared to known tailings worldwide. The economics of metal recovery may not justify full-scale tailings and mine waste processing and recovery of metals on site. Tailings and other waste on site can be upgraded and sent off, for example, to Mount Carbine. So some of the processing can happen on site and some can be sent to Mount Carbine. And then benign materials can be used for cover and rehabilitation. So the next really type of work that we would like to do on that side is focusing on how we can use that material for rehabilitation, what could be the best rehabilitation and closure plans for that particular site. Thank you, Lisa. Sorry if I went over time.
Thank you, Mansour.